So now we have to do the same sort of thing for E2 prime vector. So went ahead and crossed out this one because we're about to break that up. And we have to think about what function to evaluate here. And if you remember, for E1 prime, we used x plus iy because that was sort of an imaginary analog of this. For here, what we can use is x plus iy squared. And there's other analogs that'll work, but that's sort of like x times y, right? It's like an imaginary analog of x, y. So we're going to ask, how does x plus iy squared transform in each of these situations? Let's just expand that out. So that's x squared plus 2ixy. And then we have iy times iy, which is I squared y squared. So that gives you a minus y squared because I squared is -1. And so now we go ahead and start to do some math. And so we're asking, how does that transform? And so I think for the sake of space, I might have to erase some of this. And so what we're doing here now is evaluating, this expression, and we know for C5, right? And so we know what C5 does to x. It goes to cosine 2 pi over 5x minus sine 2 pi over 5x. We know what it does to y. It goes to sine 2 pi over 5x plus cosine 2 pi over 5y. Sorry, I think I said x here, but y. Doing the matrix multiplication. So it just ends up being a ton of math, right? And so we can walk through it. So I'm going to square that x squared term, the x squared term. So that means cosine squared 2 pi over 5x squared. That's the first term. I like doing the squared terms first. Sine squared 2 pi over 5 y squared, right? This term squared. And then it's a squaring relationship, so we know we're going to have a 2 in there. 2 cosine 2 pi over 5 times sine pi over 5 xy for the cross term. Now we have a 2ixy. So we have to times this by this. Imagine what xy does. Well, we did that previously, way in some previous part of the video. But that's going to be the first term there. We're going to have 4 terms here this time. So we're not squaring something. We have to FOIL completely. 2i cosine 2 pi over xy. That's basically the cosine terms. And then remember, we're multiplying by 2i. And then we're going to have a minus 2i sine squared, because one of the signs is minus sine squared 2 pi over 5xy. And then we have the x squared terms. So these terms go together, plus 2i cosine 2 pi over 5 sine 2 pi over 5 xy. And then we have minus 2i cosine 2 pi over 5 sine 2 pi over 5 y squared. That term is coming from these being multiplied. So now we've done plus 2i xy. Now I have to do minus a y squared. So we're squaring this, FOILing this part out. And so we get minus sine squared. Remember, it's minus everything because we're minusing x squared. Sine squared 2 pi over 5 x squared minus cosine squared 2 pi over 5 y squared minus 2 cosine 2 pi over 5 sine 2 pi over 5 xy. And now we get to simplify. And what we're going to be using extensively here is a couple of relationships. Sine squared theta minus cosine squared theta equals cosine 2 theta, and 2 cosine theta sine theta equals sine 2 theta. We're going to use those trigonometric identities, they're called, to help us. And so our first terms that we can see here are cosine squared 2 pi over 5 x squared. And then if we look for the other x squared term, it comes actually right here. So these two terms I'm going to cross out, and those are going to be able to be simplified using this relationship to just cosine 4 pi over 5 x squared. Okay, and then a similar thing we can do with sine squared 2 pi over 5 y squared minus cosine squared 2 pi over 5 y squared. Those y squared terms, we actually have a negative of this, right? Because that'll become a positive cosine squared minus sine squared 2 pi over 5. So that's going to be a negative cosine 4 pi over 5 y squared. The next one we can simplify are some xy terms. So we have these two terms. And so I'm going to cross out these two terms. They're the same. That's going to get condensed into -4. We have 2 of them and 2 of them. But it's a cosine and a sine theta. And we know we have 4 of them. Well, 2 of them equals 1 sine 2 theta. So we're going to have, since we have 4 of them, we have 2 sine 2 theta, and they're both negative. So we're going to have -2 sine 2 theta, where theta is equal to 2 pi over 5. So -2 sine 4 pi over 5. So things sort of simplify. We're getting everything into 4 pi's over 5. And then a very similar thing is going to happen with our 2i cosine squared 2 pi. Hold on a second. That's actually not the next term I wanted to do. Okay, good thing you can erase. I mean, we could have done that one, but this one is what I wanted to call your attention to. The xy terms. We have these ones. 2i sine squared with xy and 2i cosine squared, which was right here. Sorry about that. A lot of terms. And so that's going to turn, that's the cosine squared. That's the sine squared minus cosine squared relationship, but the negative of that. And so that is going to end up being minus 2i cosine 4 pi over 5 xy. And then we also have a x squared term. And where that is coming from is, sorry, there was a tiny mistake, and forgive me, this can happen. So let's look at this term. This is actually supposed to be x squared, because where that came from was 2i xy, this part here. We were doing a cross term, and it was this one times this one. Okay, and so that got x squared. But anyway, what ends up happening there is that now we can combine this using our cosine squared rule, right? Cosine squared, using our 2 cosine theta sine theta equals sine 2 theta. And so that's going to be factoring out just an I there. plus I sine 4 pi over 5 x squared. And then so that's for this one. And then last term here is a minus. We can do the same thing for this y squared term. So all of our terms are accounted for. Minus I cosine 4 pi over 5 y squared. Okay. And so now what we want to do is try to factor out our function. The reason why we're trying to factor out a function is because our original function that we tested, which, by the way, in this case is not this, but it's x plus iy squared, right? That's what we've been testing here. Sort of an analog, a squared analog of x plus iy, because we have a squared analog here in xy, quadratic analog. So we want to test to see if this is equal to something. And what it turns out to be equal to times itself, okay, is x iy squared, so our term here, times cosine 4 pi over 5 plus I, it's like a minor miracle here, sine pi over 4 pi over 5. That is epsilon squared, if you remember our derivation from a previous video. Epsilon is 2 pi over 5i, but this actually ends up equaling, when you square it, some math works out so that you get epsilon squared, and we did that in many previous parts of this video, so I don't want to waste time redoing that math. But you can walk through why this relationship is true. It's basically this term times this. So if you factor that out, you'll have x squared times cosine 4 pi over 5. That's this term. You'll have x squared times I sine 4 pi over 5. That's this term. Then you'll have 2ixy times cosine 4 pi over 5. And that's that gets you this term. And then you have actually, let's see. Yeah, there's another small sign error here. Sorry about this, but if you go through, this terms actually should be a positive. So that's why it matches, just found that error. Why is that? It came from the xy terms, which are here. And so anyway, but this ends up equaling this. So if you factor all this out, and so it's a bunch of math, but at the end, what this tells you is that you have a 1-by-1 matrix where you can take x plus iy squared, 1a squared, and there is a value. Well, what is this value? This value, as we said, was epsilon squared. So that times epsilon squared is your transformation for C5. Okay. So your character, your chi of C5 is epsilon squared. So this is probably the hardest part of this derivation, because that gets you epsilon squared here. And then from here on out, you can just kind of look at this final result here and go through and figure out what your other characters are going to be. And the way that works is you have C5-2, right, would ask what happens with C5-2, right? Well, when you do C5-2, what you started with instead of having 2 pi over 5 becomes 4 pi over 5. So all this math ends up being doubled with these thetas. So in the end here, you end up with cosine 8 pi over 5. Well, that is what? So let's do just the chi of that, the character of that. So you get cosine 8 pi over 5 plus I sine 8 pi over 5. Right? We just had to double it. Well, cosine 8 pi over 5 is the same thing as cosine 2 pi over 5. And sine 8 pi over 5 is the same thing as negative sine 2 pi over 5. And so this looks very much like what epsilon is, the definition of epsilon here, but we have the complex conjugate. The sine part is negative. So this is going to be epsilon complex conjugate. And then if we do the chi of C5 3 times, we're going to get the same thing. But now instead of 8 pi's, well, we started with 6 pi's. So we get 12 pi over 5. Well, 10 pi over 5 is a complete rotation. That's 2 pi. So we're back down to just 2 pi. And so it's going to be equal to cosine 2 pi over 5 plus I sine 2 pi over 5, which is just the definition of epsilon. So we feed in epsilon there. Then we do a C5 4 times. C5 4 times, well, we're going to get not 2 pi over 5 here, but 4 times that 8 pi over 5. That's going to turn this in when we have these trig identities to 16 pi over 5. That's really equal to then, we subtract off 10 pi over 5 because that's 2 pi, 1 full revolution on a unit circle. So now we're at cosine, this is the chi of this, cosine 6 pi over 5 plus I sine 6 pi over 5. That's equal to cosine 6 pi over 5 is equal to cosine 4 pi over 5, and sine of 6 pi over 5 is equal to negative 4 pi over 5. Well, we know this looks just like epsilon squared. Epsilon squared is basically like this, but with 4 pi over 5s. And so, but this has a negative instead of a positive. So that means we're going to get a value of epsilon squared, but the complex conjugate of epsilon squared. So that gets fed in here. And then our next part of this, we have a sigma h. And sigma h here, we are doing this formula. Well, there's a bunch of x's and y's here, but there's no z's. And we know that sigma h doesn't do anything to x's and y's. We've gone over that a bunch. So it's just going to be a 1. We're going to get back the same function. And then with the s's, just like we did previously on the E1 prime function, we know that s is just C5 times sigma h, and sigma h doesn't do anything, as we just said. So this is going to be the same character as C5. So that gets us an epsilon squared there. Same idea for S53. S53, that is the same thing as C53 times sigma h. Sigma h does nothing, so we're going to be the same character as C53, which is epsilon. And then here, sorry, running out of room. Here, S57, that is the same as C57 times sigma h. C57, sigma h goes away because we don't do anything. C57 is the same thing as C55 times C52. And C55 is identity, 360-degree rotation, so that goes away. So this is going to transform the same way under this function, at least, as a C52. So we're going to get epsilon complex conjugate of epsilon. And lastly, this by the same logic, this is going to be the same as C54. So we're going to be epsilon squared, the complex conjugate of epsilon squared. Okay, and then we have to use these rules that we did before where we know 1 plus 1 is equal to what we started with, 2 something times plus epsilon 2 squared is equal to 2 cosine 4 pi over 5. And we can look to see if we've had this before. Let's see, have we had this before? Epsilon squared plus something equals 2 cosine over 4 pi over 5. We have had that epsilon squared plus the complex conjugate of epsilon squared. We had that in E1 prime equal to cosine pi over 4. So we worked through that math previously, previous portion of the video. So we just do that, copy that over. This one, something plus complex conjugate of epsilon equals 2 cosine 2 pi over 5. We have that here with this relationship. So that's just epsilon. Again, this is very similar. So this is going to be complex conjugate of epsilon. Here, we have a similar thing where we're equaling 2 cosine 4 pi over 5. That's going to be epsilon squared. There's patterns here. Something plus 1 equals 2. It's 1. 1 plus 1 equals 2. This one, we're equaling 2 cosine 4 pi over 5. So that's epsilon. And this one's going to be epsilon squared by similar logic as we did before, epsilon and epsilon squared. And I did these just by the addition rules, but we also know that this value, this value, this value, this value should equal this value, this value, this value, this value, because sigma h doesn't do anything with this function because it contains x's and y's. And that indeed ends up being true. And so the very last thing that we need to do, I don't know, is this last thing or depends how you define being close, is we have to do this for E1 double prime and E2 double prime. And so we're going to break it up similarly, but we can use a little bit of a trick here, fortunately, to make this run faster. So I'm going to erase this all. All right, so luckily, this one is a lot simpler. And the reason why this is a lot simpler is because of the function that it transforms as. So again, what we're doing is, right, we're breaking up E1 double prime. It's 1 and 1. And the function transforms is not crazy like the one we just did, which was really hard in terms of the math. This one's times z, right? And the z transforms as the -1. So that's really lucky for us. So we know that xy times z is going to give us a function that gives us xz times yz. Well, we already broke up the xy component, that was E1 prime. So now all we have to do is copy over these and times them by A2 double prime transformation for z. Well, A2 double prime for the first 5 characters is all 1. So we're just going to copy what we had for E1 prime. So we're going to just copy that. Just copying from right here. So that is very rewarding to be able to crank through that so fast. And then the other parts here, those other 5 classes, A2 double prime or A double prime, all transfers, all transforms as -1. So we're just going to write the negatives of what we had before. So we have -1, -1. That makes sense, right? -1 plus -1 should equal -2, what we started out with. And then instead of epsilon, we're actually going to have a negative epsilon. Now you could prove this. You could go through. This is proving it. We're just doing it really shorthand, way. But your function is going to be just, xz plus iyz, right? That's something that would transform like this. But anyway, this is, way faster than do it this way. So we just do it negative of all these, negative of epsilon, complex conjugate of epsilon, negative of epsilon squared, negative of epsilon squared, negative complex conjugate of the negative of epsilon squared. That's how you actually have to say it. And we just put negative signs on all these. And fortunately, the exact same trick you can play with E2 double prime. And why is that? Well, again, we're breaking up into two one-dimensional components. And we figured out in an earlier part of the video series here that E2 double prime transformed as x, y, z. And z times x squared minus y squared. Zx squared minus zy squared. That is this function, right? Just times z. So that's E2 prime times z. So there's all these patterns, sort of how these other functions get generated for multiplying one another. But so all we have to do is multiply E2 double prime components that we already figured out above. That was the hard part. And again, the first 5 are just going to be copied for E2 double prime, which is going to be the same as E2 prime. Gotta make sure you copy this right, though. You don't want to make a mistake at this page, at this stage, right? Came so far. So this is copied. That's copied. That's copied. And that's copied. Then we have -1 and -1 again, because we have these z components trying to equal -2. But again, we just take this times that, -1 times -2. And then we're doing the negatives here because we have -1s on the z function on a double prime. Again, this came from xy times z, right? X, Y, Z. So it's going to be negative epsilon squared, negative asterisk, just negativing the E2 double prime components. And that, my friends, is the complete derivation of the C5h character table, one of the harder ones that we're going to do. Of course, they can get infinitely hard, but this is sort of still chemically relevant. And you can look at the answer here, and you can see this is the normal way they do it, where they put in terms of epsilon, which of course is equal to e to the 2 pi I over 5. It's a complex number. These are pretty nasty, but the math all works out, and all the principles that we've been going over for orthogonality. There is a special rule number 5 when thinking about the vectors components that are broken up, if you're trying to evaluate the vector components that are broken up. But these orthogonality rules, dimensionality rules, all these character table rules apply for this now just with imaginary numbers, or complex numbers, I should say, non-real solutions that all evaluate and work up, and you have complex functions that transform as these individual symmetries, and real functions that combine as basically what's linear combination, right? This component plus this component transforms as x, z, y, z, for example. So that's how this all works. Hopefully that gives you some clarity of where these complex numbers come from in this business with the e to the 2 pi over ni that you see in a lot of these character tables that have complex numbers in them.